Okay, so now we want to look a little bit at the basics of how we compute probabilities. And it's kind of important to understand there are different types of probabilities, okay? There are three general types of probabilities. The first is what we usually deal with, a formal or theoretical probabilities. And these are probabilities that we can compute exactly. So instances where we have games of chance, generally problems in physics and engineering tend to be of this form. A simple example, if you're dealt 5 cards from a deck of 52 with, what is the probability you're going to get 4 aces? Or if you roll 2 die, what's the probability you're going to get 2 6s? There's an exact answer to that, okay, given certain assumptions. However, a lot of probabilities are empirical. In other words, we have to estimate them from data. That's what empirical means, right? And usually things dealing with populations. So if we have medical, demographic, data that we're going to make probabilities from, then we have to use this sort of approach. Okay. So the probability you'll get cancer, or that you drive a VW, or you make more than $100,000 a year, these are all empirical probabilities. Okay. The last is subjective, and subjective probabilities come into play a great deal, and this is where part of computing the probability relies on someone's opinion. Usually it's an expert opinion. So anytime we're doing forecasting, the probability that something will occur in the future, that's almost always a subjective probability in some shape, way, or form. And so things that are subjective, the probability that a certain sports team will win a game, a company will be successful, things like that. Most things in real life tend to be a mixture of empirical and subjective. Okay. All right. So how do we compute probability? Well, one way is if we have a formal probability, we can compute it, and we're going to see using certain straightforward laws of probability. But very often we have empirical probabilities. And the way we're going to think of computing a probability there is that if we're interested in some event A occurring, we're going to perform that experiment some capital N number of times and count the number of times the event A occurs. And we have it in our mind that as the number of experiments becomes very, very large, this ratio of the number of times event A occurred divided by the number of experiments should be the probability that A occurred. All right? So this is kind of something that we all have in our minds. If we wanted to see whether or not a coin was fair, suppose we didn't know that it was a fair coin, how would we do that? Well, we'd flip the coin a whole bunch of times, right? Count how many times heads occurred, and that ratio we imagine would give us a good estimate as to what the probability of heads was. Now, in formal probability, it's very different, and this is the way most engineering works. It's based on what we call a probability model. And a probability model is a model where we have a way of assigning probabilities to every event in the sample space. Okay. And so there are very many models that we use in engineering. The most useful or the most common are a uniform discrete model where we have a finite number of outcomes and they're all equally likely. A Bernoulli model where we have one experiment with 2 outcomes. A binomial model where we have a sequence of independent Bernoulli experiments. A Poisson model, which is where our events occur infrequently and they're independent of each other. Okay. And finally, a normal model, which is very good for modeling the distribution of certain physical quantities or sometimes errors that might occur. Now, probability models tend to be mathematical, and this poses a problem because remember that the outcomes in a sample space may not be numbers. So we need to have some way of introducing a mapping from the sample space to the real numbers, and we call that a random variable. Okay, we're just going to map every outcome in the sample space to a real number, and that's what we're going to work with. So a random variable, like we said, is a mapping from the sample space to the reals. The way we think of a random variable is kind of like, a box of chocolates. Okay, you don't know what you're going to get until you actually bite into it. Okay, that's kind of what a random variable is. It's some property that we can't know the value until we measure it. But what makes a random variable useful is the fact that it does have a distribution. We can know the probability of getting a certain value, even though we can't know what we might get on any particular outcome. And so the one type of random variable we're going to look at is called discrete. And this is what occurs when the sample space is a discrete sample space. And as a consequence, the random variable will be a discrete random variable. And let me kind of explain how this works. Let's look at a Bernoulli process where we flip one coin. It's an experiment with two outcomes. Okay, we're going to want to make each of these a real number. So let's map heads to 1 and tails to 0. Okay? Or we could do the same with a binomial process where we're going to flip a coin a whole bunch of times. The results are independent and the probability that we get heads is the same on each outcome. That's what defines a binomial process, which we'll talk more about later. And notice that what we can do is we can count the number of times heads occurs. So every string of length n that consists of h and t can be mapped to a integer from 0 to n, right, where we're just counting up the number of times heads occurs. So this is a sort of random variable that is very useful with a binomial process. And you notice something, that very often the random variable, when we have a discrete random variable, is just counting the number of times a particular outcome that we're looking for occurs. Okay. Now we can also have continuous random variables. And remember, in a continuous sample space, okay, S is an interval, and very often in those cases we just take x to be equal to S. Okay? So if we take a uniform distribution on 0, 1, and I'll explain what this is a little bit later, the probability that x is in some interval is just the intersection of that interval with 0, 1. And we just take x to be equal to the sample space. Okay. Now notice something interesting is that it's not always the case that x is equal to the sample space. Okay. Notice if we look at IQ, the sample space is some interval. It's hard to say what it is, but let's just say for the sake of argument it's 0 to 200, right? We don't think anyone can have a negative IQ, and I don't think there's an IQ above 200. Maybe there is, but there's some upper number, right? But notice something. When we model IQ with a normal distribution, the random variable goes from -infinity to +infinity. Notice the random variable's range is not equal to the sample space. This points out something important, which is that a model is not necessarily the same as reality. Okay? It's just a very good approximation. Now, what is important about a random variable is its distribution. When we talk about a random variable, the first thing we want to know is what its distribution is. And what that means is it tells us how the values of the random variable are distributed, how they're situated. And particularly what we really are interested in is trying to get the probability that a random variable will be in a certain region. Notice this is the probability distribution for a Poisson random variable. This is a discrete random variable. And notice we kind of get an idea of where the most likely values are to occur, right? We know that the values that are most likely to occur are somewhere around 5. Okay, by the time we get out to 10, they're not very likely, right? So this is giving us an idea of how the values are distributed. We know for a normal distribution, although we'll talk about this later, that it's centered about the mean, mu. It's symmetrically located, and when we get more than 3 standard deviations away, there aren't a lot of values. So this tells us that the values are centered around the mean. Okay? And of course, we're going to get a mathematical formula for these so we can make these notions much more precise and actually use them in real problems. There are four important properties about a distribution that you generally want to know. The first is the number of local maximum. Okay, most of the distributions that we work with are unimodal, meaning they just have one local maximum. Okay, a very important property of distributions is whether or not they're symmetric. If they're not symmetric, they tend to have a tail, and we call that distribution right skewed if the tail is to the right and left skewed if it's to the left. The two last properties, which are the most important, are what we call the measure of central tendency. And this tells us basically where the center of a distribution is located. If it's symmetric, we always use the mean. If it's asymmetric, we use the median. Okay. And the last property is the measure of dispersion. This gives us a notion of how big the width of a distribution is. And this is important because if the distribution is very, very broad, the center doesn't really give us a good notion of what value we're most likely to get. Whereas if a distribution is very, very tightly peaked around the center, then we know that the mean is a very good number that's representative of what we expect to get. And the same sort of rule applies. If it's symmetric, we're always going to use a standard deviation. If it's asymmetric, we might use the interquartile range, which is the value of the third quartile minus the first quartile. However, for right now, we're going to tend to always use the mean and the standard deviation, irrespective of what the distribution is. Okay? All right, next we're going to look at a very important distribution called the uniform distribution.